Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be looking at more of sorting algorithms, and in particular we will be looking at merge sort. In the last few lectures we have been looking at various sorting algorithms, and today we will be looking at the merge sort algorithm for sorting. So, what is the problem in hand? The problem in hand is given a set S, say of integers, and we want to sort the elements in this set S. Note that this integers is just a example to be used. You can use any object for which there is a total ordering. For example, words or real numbers or any such things. Say for example, here we have been given the set S, which is 1, 4, 2, 10, 5, 8, 15, 13, 7, 8 and 1, and the goal is to sort the elements in this set S in an ascending order. So, the output that we are looking for is something like this, which is 1, 1, 2, 4, 5, 7, 8, 8, 10, 13 and 15. So, note that this output elements are in a ascending order. So, sorting is one of the most studied algorithms in this subject, and in fact there exists a huge number of sorting algorithms which are used for various different kind of settings and so on. In this lecture series we will be looking at only a handful of them and try to understand when is one better than the other. In the last two lectures we saw insertion sort and quick sort, and in this lecture we will be looking at merge sort. Now, to recall, for insertion sort we had this simple pseudocode. The idea was simple: you take an element one by one out of S and insert into a sorted list T, and since T is sorted, you just insert it in the right place and you still get a sorted list, and continue till you have exhausted all the elements in this set S. So, for insertion sort we saw that the running time was something of the form n square plus 3 n by 2, whereas the space complexity, actually we did not have to use any additional space for array or something, but we used some indices like index like I, j and so on, which requires log n space. So, the space complexity was log n, and the obvious question was, can we improve the runtime while keeping the space complexity log n, and the answer was yes, in some sense, in some direction, and let us quickly see what our idea was. The idea was this quick sort algorithm. In quick sort, the idea is simple: you pick an element x from this set S and call that one a pivot, and then keep all the elements that are less than x to the left of x, all the elements larger than x to the right of x, and then sort the elements left of x and the right of x recursively. So, for example, if we have this set 12, 4, 2, 10, 5, 8, 15, 13, 7 and 8, the 12 is the pivot. So, we take the pivot and put it in the middle, and then we go through this set S and write down all the elements in set S that are smaller than 12 to the left of 12 and things which are bigger than 12 to the right of 12. Thus, we have this set, and now recursively we can sort this set of elements which are left of 12 and the set of elements to the right of 12. Thus, if you sort the ones that are left, we get something like this, and then if you sort it the ones that are in the right, we get something like this, and now this gives us the complete sorted list, because the elements in the left are sorted and are less than 12, and elements which on the right are greater than 12 and are sorted also. So, this gave us the pseudo code, which was kind of simple. Again, we just took the pivot, we went through the set S and split this set S into two parts, R and L, and then we recursively called quick sort L, then output X, and then we recursively called quick sort R again, and the final one is our sorted list. So, we saw in the last lecture that this quick sort algorithm correctly sorts this set S. It has a time complexity of around the same thing of the insertion sort, which is n squared around, and the space complexity, since we had to create these two sets L and R, it required n. Then again we looked at a improved version of this quick sort, and such that we can create this L and R in the same list, and in that case we can reuse this space and thus get the space complexity down to log n. And we also saw that we can randomize the quick sort, but instead of picking the first element as the pivot, if you pick a random element as the pivot, then we can obtain our expected runtime of n log n. And this is where we stood for quick sort case, that we have a worst case runtime of around n square, the space complexity is log n, and the worst case and expected runtime is n log n. And this was the comparison between the quick insertion sort and the quick sort. Now, the question is, can we do better than quick sort, in the sense that can we obtain an algorithm where the worst case running time is n log n. To understand whether that can be done, let us revisit the time complexity proof for quick sort, and then we will understand how one can hope to improve it. Okay, here is in the left we have the quick sort algorithm, the pseudo code for quick sort algorithm, and on the right let us go over the proof of the time complexity for quick sort. So, let Tn be the time complexity for sorting a set of n elements using quick sort. Now, to split this whole set S into L, R and L, we required around n steps here. So, the number of steps required to split it into R and L was n, and then we called this quick sort L and quick sort R recursively. Now, since T n is the time complexity for sorting an set of n elements, so what is the time complexity for sorting L? It is, of course, it is T of size of L, and similarly this one is T of size of R, and thus we have T of size of S is n for this set plus T of size of L plus T of size of R. And then we claim that in the worst case the size of L can become 0, whereas the size of R can be n, and then we get T of n equals to n plus T n minus 1, and then we went on to prove that T n will become n square around, because this will be n plus n minus 1 plus n minus 2 and so on. But if somehow we could have picked up some pivot or something like that, such that size of L would be size of R around same, so the worst case will not occur, then we are in a better shape. So, if note that this is a very hypothetical if, we still do not have any idea how to get this if, but if somehow somebody could have ensured that the size of the left set and the size of the right set was n over 2, then we would have got T of n equals to n plus twice T n over 2, and in that case if T n equals to n plus twice T n over 2, then we can write also T n, we can just break it up once again, it is n plus 2 times n over 2 plus twice T n over 4, which is T of n equals to 2 n plus 4 times T n over 4. And if you keep on going like this, we get T of n would become equals to k of n plus 2 to the power k T n by 2 to the power k. And once we have this kind of situation, then if we put k to be equals to log n, then we have T of n equals to n times log n plus 2 to the power log n times T n by 2 to the power log n. Note that 2 to the power log n is n. So, what do we get? N log n plus n times T of 1. Now, this is a significant improvement, because n times log n plus n T of 1 is less than twice n log n, and this is much less than n square. So, if somehow I could have guaranteed that this set was split up in some equal sets L and R, I would have been in a good shape. So, can we use the same idea to improve our algorithm for and obtain such a bound? Now, the first and most natural thing to do is, okay, we have to split our set S into two equal halves. Till now we were picking an element and we are splitting it according to the pivot. But what happens if we just brute force split it? Like for example, we have 12, 4, 2, 10, 5, 8, 15, 13, 7 and 8 be the set S, and we just split it up right in the middle. So, we take 5 elements in this side and the left side and 5 elements on the right side. So, we have 12, 4, 2, 10 and 5 on the left, and 8, 15, 13, 7 and 8 on the right. Now, of course, recursively we can sort each of them. So, we sort the ones in the left and we sort the ones in the right. Good. So, here we are. We have taken a set S, we have split it up into two halves of equal size, we have recursively sorted them. This sounds very similar to the one we did for quicksort, except that in quicksort there was a pivot which kind of ensured that ones on the left is always less than the ones on the right, and thus we could have output just the merging of these two sets sorted list. Unfortunately, we cannot do it here, because note that 12 is greater than 7. So, if you just merge these two sets, then we would not get a sorted list. So, if we have to make this idea work, we have to talk about how to merge two of this sorted list into one sorted list. We will take a short break now. After we come back after the break, we will look at how to merge two sets. Welcome back after the break. Before the break, we looked at the possible ways of improving the quick sort algorithm, and the idea that we had was we take the set S, we split it up into two halves equally, and then we sort each of these halves recursively. But then we had two sorted lists, and we have to somehow merge these two lists into one sorted list. So, how to merge these two lists? Here is this algorithm for this merging. I will again explain this merging using this example, and I will ask you guys to go back and write up the pseudocode. This will be the question for this lecture. So, to start with, we want to merge these two following sets. So, to for start, we want to have some end of the list marker, and which we end up saying that we will put some infinity at the end. This is infinity is nothing but saying that it is something very large object which will not cause any problem to our list, and it is just as an end of the list marker. Now, we also start with marking two numbers here, 2 and 7, the first two elements. What do? We compare between 2 and 7. Note that this list on the left is sorted and this list on the right is sorted, and we are taking the two of the smallest elements in both of this list. Now, the smallest element of this two list between 2 and 7 therefore must be the shortest smallest element in the whole set S. So, what we do? We compare 2 and 7, whichever is less, in this case 2, we output it in the below. Now, once we are done with 2, so we can move our marker. So, our marker was here, and we move our marker from 2 to 4, and we remove this 2. So, from now on we can think that this 2 is gone, it is not there. We have already taken care of this 2 because we have taken the 2 down, and it almost recursively comes down to merging two sets, which is in this case 4, 5, 10 and 12, and this set 7, 8, 8, 13 and 15. Now, both of these sets are again sorted, and we compare this 4 and 7, and whichever is small we write down, because note that in this leftover lists the smallest one of this first two will be the smallest one among all the rest of the elements. So, here 4 will be the smallest, and thus we output 4 below. We keep on going like this, and again we have 7, we move our marker to 5, we compare 5 and 7, again 5 is the smallest, we output the 5 at the below, and we move our pointer from 5 to 10. Now, at this point we have 10 here and 7 here, and we compare 7 with 10, and what is the smallest smaller of these two numbers? It is 7. So, we output 7, and we move our marker from 7 to 8, the right marker from 7 to 8. Now, we compare 8 and 10, again 8 is the smallest. So, we output 8, and we move our marker from the first 8 to the second 8. Again we compare this 8 with 10, we output the smaller of these two, which is 8, we move our marker to 13. Now, we compare 10 with 13, we find that 10 is smallest, we output 10, we move our left marker from 10 to 12, we compare 12 with 13, 12 is less, we output 12, we move our marker from 12 to infinity. Now, we compare 13 with infinity, now 13 is smaller than infinity, so we output 13, and then we move our marker to 15, and we compare 15 with infinity, and we mark our output 15, and then the right marker also reaches infinity. When both the markers reaches infinity, this game over and we have output the merged list. So, here is the pseudocode of this algorithm of this merged list, and it is exactly what I just described. We just maintain two markers, one for the left half, one for the right half, and we slowly move one by one. And we always compare the smallest of these two, whichever is the smaller, we will output that one in the array. So, note that here I leave it as an exercise to check that this algorithm will work and will output the merged version of these two lists. Note that the output list will also be sorted, that is how the merging happens. The time complexity, note that I have this set L and R, L plus R is 10 n, and we moved the left pointer from the first element of the set to L to the last element, and similarly for the right marker. So, this both the markers total have travelled n distance, and thus the time complexity will be n. The space complexity will also be n, because when we merge these two things, we have to output this merge list into a new place, correct, wherever we are storing that numbers. And so, this array has to be maintained, and thus the space complexity of this algorithm is n. So, if we go back and look at the merge sort, how do we do it? This is, recall that this is the same idea that we had earlier. The idea is simple. We call it a recursive algorithm. So, we have a merge sort with input S, which is the set I and j. So, the goal is to sort all the elements in this set S from index I to index j. So, if I is equals to j, that means the set S has only one element. In that case, we just output the set S. Else, we compute the midpoint between I and j. So, I plus j by 2, and let us call U to be the merged sort of S, I and M. So, I sort the left half, U is the sorted list of the left half. Similarly, V is the sorted list of the right half, and then we merge the U and V, and that would give us the sorted merge sort algorithm. So, we will do this merge sort. Note that I will not do the proof of this algorithm, I leave it to you guys to check again, but let us do the time complexity of this algorithm. Let us T n be the time complexity for sorting the set of n elements. So, what is the time complexity? Note that to merge these two sets U and V, I will need order n steps. So, number of steps required for merging is n. Thus, T n will be n, which is for this merging, T n by 2, this is sorting sort U, and T n by 2, which is sort phi. This is because we have been calling this merge sort U and merge sort V recursively. And once we have this, so n T n equals to n plus twice T n over 2, this is exactly the same analysis we did before, and in that case we had got T of n is less than or equals to twice n log n. Now, in the space complexity of merge sort, since merging itself takes space n, we cannot do anything but use this space n. So, the space complexity of this merge sort algorithm is n. So, to summarize, the merge sort S1 n will sort the whole list. The time complexity will be twice n log n, whereas the space complexity will be n. Let us compare here with the other ones. In the insertion sort, the worst case running time was around n square, which was also a same case in this quick sort algorithm, but in the merge sort we have gained a lot in these times of worst case runtime, and we have gone to twice n log n. N squared to n log n is a huge jump. In the space complexity, whereas insertion sort and the quick sort both took log n, but the merge sort took n steps in space complexity, and the quick sort in the middle also showed that in expected runtime quick sort requires n log n steps. So, here we are, it is a very common question to ask which of these sorting algorithms are good. One thing to note is that in most of the cases quick sort is better than insertion sort, because in terms of parameters it is clearly better, but insertion sort, as we had seen couple of lectures earlier, had some other properties which quick sort or merge sort do not have. As comparison between quick sort and merge sort has surely a much better time complexity than quick sort in the worst case running time, but space complexity quick sort is better. Also in general it has been seen that since the expected runtime is n log n, so there are many times when the quick sort performs significantly better than merge sort even in terms of time complexity. In the worst case runtime, theoretically merge sort is the algorithm to be chosen. Many times in practice people do use quick sort. So, this ends up the comparison of these three most commonly used sorting algorithms. In the next lecture we will see some more sorting algorithms and some sorting algorithms for which the structure of the set is also very important. So, to summarize, in this talk we saw how to merge two sorted lists into one list, and then we saw how to use those two lists, this merging algorithm to do the merge sort algorithm for sorting. So, we end this talk now. We will continue on sorting algorithm in next class. Thank you.